The black hole may not be unfamiliar to you, but have you ever heard of a black ring? We know that although it's called a hole, a black hole is not a two-dimensional opening. In fact, it is a three-dimensional sphere that can be entered from any direction, or rather, a three-dimensional hole. Otherwise, why would so many people say that a black hole shouldn't be called a black hole, but a black sphere? If you think the same way, then your understanding of black holes is still too narrow. Who says a black hole must be a sphere? For a very long time, physicists believed that although black holes are mysterious, their nature is actually quite simple. To fully describe an ordinary object, we often need to consider its internal structure, material composition, elemental makeup, and even the arrangement of molecules and atoms. But a black hole can be completely described using just three physical quantities: mass, angular momentum, and electric charge. This is known as the no-hair theorem. Here, hair refers to all information other than these three basic quantities. As for the shape of a black hole, it was thought to be highly uniform, whether round or slightly flattened. In the end, it is always a sphere. This is known as the horizon topology theorem. For this reason, the no-hair theorem also has another name, the black hole uniqueness theorem. That is, once you know how massive a black hole is, how fast it spins, and how much charge it carries, its appearance is completely fixed. It can only be a sphere, and no other shape is possible. However, all of this is built upon the four-dimensional spacetime we are familiar with, 3 dimensions of space plus 1 of time. Einstein's field equations, as universal equations based on differential geometry, do not impose any restriction on dimensionality. Moreover, in some theories, our universe may contain higher dimensions. For example, according to string theory, the universe may have 10 or even 11 dimensions. So if extra dimensions do exist, would black holes still be spherical? In 2001, 2 physicists, while studying Einstein's field equations in 5-dimensional spacetime, unexpectedly calculated a monster, a black hole shaped like a donut. This type of black hole also has an event horizon, but the horizon is hollow in the middle, and curls around into a ring. Thus, it is called a black ring. We once believed that as long as mass, angular momentum, and electric charge were fixed, the shape of a black hole must be spherical. But who would have thought that in 5-dimensional spacetime, a black hole could have an entirely different appearance? The black hole uniqueness theorem failed. Why can a black hole become a donut in 5 dimensions? To understand this, we first need to understand why a black hole in 4-dimensional spacetime can never be a donut. The reason is actually quite simple. If you want to turn a spherical black hole into a ring, it must rotate, and it must rotate extremely fast. But rotating black holes are nothing rare. Stars already carry angular momentum. After collapsing into black holes, due to the conservation of angular momentum, their rotation speeds become extremely high, as their radii shrink to tiny scales. So why do these black holes only flatten, instead of turning into rings? Is it because they still don't spin fast enough? You should know that no matter how fast a black hole spins, it can never exceed the speed of light. So the fundamental reason the event horizon cannot become a ring is still gravity itself. Gravity is simply too strong, no matter how fast the rotation. Inertial centrifugal force can never overcome gravity. If you were to forcibly rotate faster than light, the event horizon might not survive at all. Once the horizon breaks, setting aside whether the area theorem would allow it, the singularity inside the black hole would be exposed, creating a naked singularity, which is also forbidden in physics. So why does this become possible in 5-dimensional spacetime? Because there is one extra spatial dimension. This gives gravity an additional direction in which to spread. As a result, gravity decays faster with distance. Once gravity's binding strength weakens, and centrifugal force gains the upper hand, the black hole can be flung into a hollow ring. In other words, in 5-dimensional spacetime, if a black hole rotates slowly, it remains spherical. If it rotates fast enough, it turns into a ring, and the faster it spins, the thinner the ring becomes. Yes, black rings also come in fat black rings and thin black rings. However, as a donut-shaped black hole, a rapidly rotating black ring is actually unstable, extremely fragile. In fact, it's like turning a faucet to a very low flow. A thin stream of water is hard to keep continuous, and easily breaks into droplets. Black rings behave in much the same way. Those extremely thin black rings are highly unstable. The slightest disturbance can cause them to snap or collapse into a lump. Given that large-scale black rings cannot exist stably, and that we currently believe there are no extra dimensions at macroscopic scales, does this mean black rings cannot exist in our universe? If large black rings are unstable, what about tiny, microscopic black rings? Some scientists have found that at microscopic scales, Quantum fluctuations can provide a degree of stability. This suggests that at the microscopic level, a large number of tiny black rings may be drifting through the universe all the time. Beyond microscopic black rings, in theory, we might even be able to stabilize black rings artificially. The general idea goes like this. Black rings are unstable, because their own gravity and centrifugal force are difficult to balance, but if we place some matter around them, the additional gravity produced by that matter might help bring the system into balance. Under the right conditions, even a nearly non-rotating, static black ring could exist stably. This kind of black ring is called a distorted black ring. If black rings can exist, could black holes have other shapes as well? The answer is yes. Some scientists have once compiled a list of allowed black hole shapes. In this list, besides spheres and rings, there is another special type, called lens space. A lens space can be roughly imagined as a folded sphere. If you can't picture it, that's fine. Scientists themselves can't really visualize it either. It is more of a definition from a mathematical perspective. In short, it is a complex geometric object, with a more intricate, twisted internal structure than a donut. You can call it a lens black hole, or simply a black lens. Although scientists have derived the possibility of lens black holes on paper, no one had ever found a perfect mathematical solution. Either naked singularities would appear, or conical singularities with spacetime creases would emerge. In short, they could not exist stably. However, in 2023, two mathematicians from Stony Brook University in the United States found, for the first time, a lens black hole solution that satisfies all the rules and contains no spacetime defects. They realized that previous attempts were too fixated on searching for solutions directly within five-dimensional spacetime, so they came up with a clever workaround. By introducing something called Kaluza-Klein matter, they elevated the problem to a higher dimension. Kaluza-Klein matter is essentially an effective form of matter that naturally emerges when a higher dimensional vacuum is compactified into lower dimensions. In other words, the folds of space in higher dimensions manifest as matter-like properties in lower dimensions. If that doesn't make sense, don't worry. The key point is, they raised the dimensionality. Why raise the dimensionality? Because as dimensions increase, the structure of spacetime actually becomes simpler. So they searched for solutions in this newly constructed higher dimensional space. After solving the equations by tuning parameters, they then found ways to hide the extra dimensions and reduce the dimensionality again. Through this process, first going up in dimensions to solve the equations, then coming back down, they successfully found a black lens solution in five-dimensional spacetime. More importantly, this method is extremely general. Not only lens black holes, but spherical ones, ring-shaped ones, and even various combinations can all be constructed using this approach. It can be seen as a universal key to high-dimensional black holes. At this point, many people may wonder, what is all of this actually good for? We haven't even fully figured out black holes in 4 dimensions yet, and we're already studying 5-dimensional ones. In fact, modern physics has long passed the stage where theory merely follows experiments. Discover an effect today, build a theory tomorrow. That era is over. Today, theoretical physics runs far ahead of experiments. Many phenomena are first discovered in theory, and only much later verified in reality. Some predictions may not be testable, even in the foreseeable future. The study of black holes is no exception. Its value is not that we can build a spaceship tomorrow and go visit one. Its value lies in how profoundly it expands our understanding of gravity and spacetime. After all, the true nature of the universe is far richer and more colorful than what we can directly perceive. See you next time. Bye.